Hey everyone, let's solve today's LeetCode POTD. Count the number of computer unlocking permutations. We are given an array complexity of length n, which denotes that we have n logged computers in the room with labels from 0 to n minus 1, the indices of the complexity array. Now each has its own unique password, means, and the password of the computer I has a complexity of I. Hence we are given a complexity array which denotes the complexity of each computer from 0 till n minus 1. Now for the computer 0, the password is already decrypted. Okay, and it will serve as the root to solve or decrypt the password for other computers. Now how can we decrypt the passwords for other computers? So for if you want to decrypt a password for computer I, then we should have already decrypted a password for a computer J whose label is less than I, as well as we should have complexity of J less than complexity of I. That means if we want to if we have already decrypted a computer with value x, then for our I, the complexity of I should be greater than x. Okay, so to decrypt the password for I, we must have already unlocked a computer J such that J is less than I, as well as this should also follow that complexity of J should be less than complexity of I. Now we know this 0 is fixed, means this is the first person to get decrypted. Now what about the remaining values from 1 till n minus 1? So we can unlock them in some fashion, right? Maybe 2 comes first, then 4 comes first, then 3 comes first, and so on. Or this 4 comes first, then 3 comes first, then 2 comes first, and so on, right? So there can be multiple answers possible. So we need to return the number of permutations of the results that will represent a valid order in which the computers can be unlocked. And since starting from 0, because 0 will be the first computer that will be unlocked. And since we know n can go up to 1e5, so these total permutations may go up to n factorial, means n minus 1 factorial. So hence if it means is over integer values, we will simply return it modulo 1e9 plus 7. Okay, so let's see the given input. So we are given 3 computers of complexity 1, 2 and 3. So if we unlock the computer with complexity 0, so here its complexity is 1. Okay, now we have unlocked computer 0. So either in the next step we can unlock computer computer 1 or try to unlock computer 2. Now if we try to unlock computer 1, we see that its complexity is 2, and hence there exists a j less than I, means there exists 0 less than 1 such that 1 is less than 2. That means complexity of j is less than complexity of I. Hence it is possible to unlock this computer 1 using computer 0. Okay, so we'll be able to unlock computer 1 using computer 0 with value 2. Now for computer 2, whether we'll be able to unlock it or not, so we see that its complexity is 3 and we will be able to open it using either computer 0 or computer 1, because both of these values are less than 3. So hence we'll be able to open this computer as well. So this represents one of the valid orderings. Now instead of opening computer 1 first, let's try opening computer 2 first. So we see computer 0 has a value 1 and this has a value 3. So we see 1 is less than 3. That means we'll be able to decrypt this computer. So this will be able to decrypt. Now we need to decrypt computer 1. So again its value is 2. And we see we have a computer 0 whose value is 1 and 1 is less than 2. Hence we will be able to decrypt 1 in the third place as well. So these are the two possible ways of decrypting. Hence the number of total permutations for this input was 2. Let's see another input. So we are given 3 3 3 4 4 4. So we are given 6 computers from 0 to 5, and initially this 3 is unlocked. Okay, so 0th index is unlocked with value 3. Now what computers can we unlock on the basis of this 3? Okay, so we can only unlock computers which has a complexity of j greater than complexity of 0, right? So using like using this 0th computer, we'll be able to unlock all those computers who have a value greater than this 3. This means 4, 4 and 4. Means the computer 3, 4 and 5, since they have a complexity value greater than complexity of 0, hence we will be able to decrypt these computers using the value of computer of 0. Okay, so we can like fulfill the conditions of 3, 4 and 5 in any order. Okay, either 3, 4, 5 or 3, 5, 4, then 4, 3, 5 or 4, 5, 3 or 5, 3, 4 or 5, 4, 3. Okay, so we can like satisfy the condition for these 3 computers in any order. Now comes the remaining computers 1 and 2. Okay, so for 3, now both 1 and 2 has a complexity of 3. So we need to see whether there exists a computer with complexity less than 3. Okay, so we see like there exists no computer which we have already encountered before and has a j less than I, means for 1 it should have 0, means comp 0 should be less than comp of 1, but this is not true, right? So hence we will not be able to like decrypt these computers 1 as well as computer 2. So hence even if like there were 6 possibilities of unlocking computers 3, 4 and 4, 3, 4 and 5, we were not able to like decrypt all of the computers. Hence the total number of valid permutations here would be 0 only. Okay, so like what can be the means the most brute force approach of solving this? So we know like the 0 is fixed. Okay, computer 0 is fixed. Now for values from 1 till n minus 1, we can arrange them in, we need to find the all the permutations which are valid. So we can try iterating through all permutations of 1 till n minus 1, right? Once we try iterating through all possibilities of permutations of 1 to n minus 1, then we'll see the condition check, okay, for each permutation. Now what is the condition check? The condition check is that initially we have the mini complexity as comp of 0. Okay, so we'll iterate for this permutation from the values that are represented. Suppose it was represented as j1, j2, so on till jn minus 1. Okay, so we need to make sure that the value of comp of j1 should be greater than mini, so that we can use this mini to unlock this comp of j1, right? Then once we have unlock this, then for comp of j2 we need to make sure that it is also greater than mini. Okay, so either it is like simply greater than mini or it is greater than both of them. Okay, so that we can use any of these two computers. So we'll keep doing the check till the end, and if it is satisfiable for all the indices from 1 till n minus 1, then we'll return, means increase our result by 1. Okay, and as you can see, like the number of valid permutations from 1 till n minus 1 can go up to n minus 1 factorial, and for each check we'll be using, means iterating through the array ones to n, so it will be like n into n minus 1 factorial, which will be of the order of n factorial. And as you can see, like n can go up to 1e5, so this will definitely give us TLE here. Okay, so now how do we like try to solve this problem, because n factorial is very huge and we need to think of something optimal here. So we can try to make some observations here. So we see that 0 is the root parent here. Okay, 0 is the root computer here. Now using this 0th computer will definitely be means decrypting some of the computers, right? So we'll be decrypting, let's say we decrypt these computers j1, j2 till jk. Now all of these values from will have the complexity of ji, it will have greater than complexity of 0. Okay, so for all of these computers will definitely have the complexity greater than complexity of 0. Okay, now once we have unlocked these many computers, we need to see like whether we had the subset of 1 till n minus 1 and j1 j2 till jk was a subset of this. So let's say if this was s and this was like s dash. So for the remaining subset of s dash minus s, we need to see how we'll be able to unlock it. So suppose that subset is, suppose k1, k2 till km. Okay, the new values are. So now we need to make sure that these values are, means the complexity of ki should be greater than the means the computers we have already unlocked, and that means it should be greater than what? It should be either greater than complexity of 0 or greater than complexity of j1, means or complexity of j1 or complexity of j2 and so on till complexity of jk. Okay, and now we see like complexity of j1 j2 jk till jk, these are all greater than complexity of 0, right? Hence what do we reduce? We reduce that complexity of ki should be greater than complexity of 0 only. So we are not dependent on these, means the values that we have unlocked in the first step. We are not dependent on these values. We are only dependent on the complexity of 0. And if the complexity of 0 is less than complexity of ki, and here ki is a general index, right? So this ki can be anything. So if for every index complexity of that index is greater than complexity of 0, then we can unlock in any order, right? We can unlock in any order. And if there exists a case like if any index exists such that what? Such that the complexity of index is less than equals to complexity of 0. So in this case, if there exists any index which means follows this manner, then there will be no valid permutation size. So in this case, we will simply return 0. Why there exists no permutation? Because we'll need to use this complexity of 0, and it should be like the minimum possible value. It should be less than all of the remaining values, means all of the values from 1 till n minus 1. Because we will be using complexity of 0, means the 0th computer only, to solve, means decrypt all of the remaining computers. And if any of the computers satisfies, like we have the array as 1, then we have 2, 3, 4, 5, and then we have again 1. So we will be able to, means this is a 0th computer, so we will be able to decrypt all of these computers in any fashion, because all of these values are greater than complexity of 0. Okay, so we'll be able to decrypt them in any order. So suppose here we have 4 factorial ways, but for this one we see like 1 is less, means it is not greater than 1. So hence we will not be able to decrypt this computer using any of the computers we have unlocked so far, and the means obviously we will be using the complexity of 0 only to like decrypt any computer. So if this condition is satisfied for any of the computers, then we know that there exist no valid permutations and we will simply return 0 in this case. And else what do we return? We can need to like, then we can unlock in any order. So hence from 1 till n minus 1 we can unlock them in any order, and that order will be simply n minus 1 factorial. And since this value can go up to like very huge, like till long, so then at each step we need to take this n minus 1 factorial percent mod, where mod here is 1e9 plus 7. So I hope you are able to like observe on the basis of like, if we try to decrypt a first set of computers, we saw that all of these values should be greater than complexity of 0. Then if we try to decrypt a new set of values other than them, then we see like these values should be either greater than all of them, and since it should be greater than all of these values, and these all values should be greater than complexity of 0 only. So that means the new set should also have all the values greater than complexity of 0 only. Hence from this we can derive that if all the values are greater than complexity of 0, then that means we can decrypt them in any possible manner. And if any of the computers does not satisfy the condition of being greater, then we can simply conclude that the number of ways is simply 0, because we will not be able to decrypt that particular computer. So hence what do we need to do? We simply need to do this check, and if it is satisfied for any condition, we will simply return 0, and else we will simply compute n minus 1 factorial. And how will we be computing it? So we will simply update, means keep track of products from all elements from I till n minus 1, and at each step what we will do, we will update our result with result into I percent mod. Okay, so this is what we need to do. And yeah, so this is pretty much it, and this will be like order of n solution, and as you can see, like n can go up to 1e5. So this will be the most optimal solution for this problem. So let's see the code as well. So we have like the complexity array, we define the mod 1e9 plus 7. Now the root complexity is complexity of 0. So we see like if this condition is satisfied, like the complexity of I is not greater than the root complexity, then we simply return 0, means there exists no possible ways of means arrangement. And else we will simply initialize this result with 1 and keep updating it with 1 into 2 into till n minus 1, so that it represents n minus 1 factorial. At each step we will be taking the mod to keep it in the range, and we simply return this result. So this is the as you can see, like this takes big of n, and yeah, this also takes big of n. So the overall complexity is big of n only. Let's try to submit the code as well here and see like how much time it takes to run. It should run like very fast. As you can see, it runs in 0 ms because like 1e5 is pretty fast. So I hope you were able to like make observations and follow the approach. And if you did, make sure to like as well as subscribe. And if you have any doubts remaining, feel free to comment down and I will be happy to help. Thank you so much for watching.